Hello everyone, welcome to our session. Today, we are beginning an exciting journey into the heart of machine learning. Our first stop is understanding a fundamental concept called gradient descent. Technically, gradient descent is an iterative optimization algorithm. It's the process our computer uses to find the absolute minimum of a function, effectively searching for the lowest point in a landscape of possibilities. To build some intuition, let's use the hiker analogy. Imagine you are standing on a mountain peak, surrounded by thick fog. You want to reach the valley at the bottom, but you can only see the ground beneath your feet. To get there, you'd feel the slope and take a step in the direction that goes down most steeply. You repeat this, step by step, until you can't go any lower. In machine learning terms, our goal is expressed by this formula, minimizing the cost function j of theta. This cost function measures how much error our model is making. By minimizing it, we are essentially maximizing our model's accuracy. This mechanism is absolutely fundamental. It is the engine used to train everything from simple linear regressions to the most complex neural networks used in modern AI. Now that we've seen how gradient descent acts as the engine for AI training, let's look under the hood at the mathematical foundation that makes it all possible. Everything starts with understanding the slope sign. If the slope is positive, the function is increasing. If it's negative, it's decreasing. This is the simplest clue for our optimization process. To calculate this precisely, we use the derivative. As Leo likes to point out, the derivative tells us the rate of change at a specific point, essentially giving our hiker the direction of the slope at their exact coordinates. In machine learning, we aren't just dealing with one variable. We have many weights and biases. We use partial derivatives to see how sensitive the loss function j is to changes in each individual parameter, like this weight w shown here. Finally, we combine all those partial derivatives into a gradient vector. It's important to remember, the gradient points in the direction of steepest descent. Since we want to minimize loss, we'll actually be moving in the opposite direction. Keep these concepts in mind, because next, we're going to put your intuition to the test to see how these slopes guide our path. Building on the intuition we just established, let's translate that hiker descending a mountain analogy into the precise mathematical language of the weight update rule. This formula is the engine of gradient descent. It defines how we modify our model's parameters in every single iteration to minimize the loss. On the left side, we have our target, the new weight, Wt plus 1. This is the adjusted value we hope will lead us closer to the global minimum. We calculate it by taking our current weight, Wt, and subtracting an update term. But why the subtraction? As we've noted, the gradient points toward the steepest uphill direction. To go downhill, we must subtract the gradient, effectively moving in the opposite direction. We then scale this movement by alpha, the learning rate. This hyperparameter acts as our step size, ensuring we don't jump too far and overshoot the valley floor. This update repeats hundreds or thousands of times. We stop once we reach convergence, the point where the weights stop changing significantly because we've found the bottom. Next, let's see this formula in action with a simulation. Welcome! In this simulation, we'll explore how the learning rate controls how we navigate a loss function to find its minimum. The learning rate slider adjusts the step size. A larger value means bigger jumps down the slope. With an optimal learning rate, the ball moves efficiently toward the bottom, achieving fast convergence. Notice how a very small learning rate makes the process slow. The ball takes many tiny steps and takes much longer to reach the bottom. Watch what happens when the learning rate is too high. The ball overshoots the minimum, bouncing back and forth between the walls. Now it's your turn. Try to find the exact point where the learning rate becomes so high that the ball diverges and flies out of the curve. Having just played with the simulation, you've seen how sensitive the descent is to the step size. Now, let's formalize the logic behind choosing the right learning rate. In our update rule, alpha acts as the scaling factor. It determines the magnitude of the change we apply to our parameters based on the current slope. As noted here, if we set alpha too small, we face slow convergence. It's like a hiker taking tiny millimeter steps. They will eventually reach the valley, but the computational time would be massive. Looking at this chart of loss versus iterations, we are aiming for the Goldilocks zone. Too high, and the loss will oscillate or diverge. Too low, and the curve stays flat for far too long. We need that perfect middle ground for efficiency. Now that we have the right learning rate, we need to decide how much data to look at before making an update. This brings us to the three main variants of gradient descent. Look at this comparison. Batch gradient descent uses the entire dataset for one update. It's stable, but as we scale to millions of images, it becomes a memory nightmare. Stochastic gradient descent, or SGD, updates after every single example. It's fast, and the noise helps it escape poor local minima, though it never truly settles. Despite these differences in data usage, notice that the universal update rule we analyzed earlier remains exactly the same. We are still subtracting the gradient from our current parameters to find the minimum. In practice, mini-batch gradient descent is the industry standard. It strikes a balance by using small subsets of data, allowing us to leverage powerful GPU matrix operations for speed, while maintaining stable convergence. To wrap up our session today, we need to address the actual landscape our algorithm navigates. As we've seen on previous pages, the loss function isn't always a simple, smooth bowl. In simpler models like linear regression, we deal with convex functions. These are ideal because they have a single global minimum, guaranteeing that if we tune our learning rate correctly, we will reach the absolute best solution. However, in complex architectures like neural networks, we face non-convex functions. These landscapes are filled with multiple valleys, plateaus, and peaks, making the descent much more treacherous. The biggest risk here is getting stuck in a local minimum, a point that looks like the bottom to the algorithm, but is actually suboptimal compared to the global minimum. We also have to watch out for saddle points, where the gradient is zero but we haven't reached a minimum at all. To overcome these, we use advanced optimizers like momentum, atom, or RMsprop. These methods use the history of the gradient to help skip over shallow plateaus and push past local traps. That brings us to the end of our deep dive into gradient descent. We've covered everything from the mathematical foundations and the update rule to different batch variants and finally, the challenges of optimization landscapes. Great job today, everyone! Keep practicing these concepts as you build your models,